Okay, well, good afternoon, everybody. Welcome to our May webinar where we're going to be, or we're not going to be, Tim Dunton with Reliability Solutions is going to be talking about root cause analysis or problem elimination. So we're glad that you've joined us today. Tim is actually going to be presenting at our Reliable Asset World Conference coming up in just a week and a half now, which is co-located with our 11th annual Ultrasound World. Tim's been a presenter at our conferences for at least the past couple years that I'm aware of, and so if you like what you hear today, hopefully if there's still a chance for you to get down to Florida, you can come and join us. Otherwise, you can see the previous presentations that he's done for us up on our website. We've got those archived there, so opportunities to continue learning from Tim after the webinar concludes today. Just a couple housekeeping things. We are recording this, so if you have to hop off early or you've got colleagues that couldn't make it, we will have this up on our website, so you can take a listen again later on a time that works for you. So we'll have that for you. And also, we do have the ability for you to ask questions. You'll see in the little panel on your right-hand side of your computer, there's a little questions box. Feel free to type in questions that you've got throughout the presentation. I'll jump in and get those questions answered by Tim. As it makes sense. So we try and make this as interactive as we can with folks spread out throughout the globe here. So take advantage of that, and we'll definitely have some time also at the end for Tim to do some Q&A with us. So that being said, I'm going to turn things over to Tim and let him take it away. Thanks, Tim, for joining us today.
Thanks, Maureen. Let me just get my screen going. Hopefully everybody can see the screen now. Welcome, everybody, and thanks for joining. And again, I thank Maureen and Doug and everybody at UE Systems for the opportunity. What I want to talk about today is this whole process around root cause problem analysis and sort of how it kind of works within reliable manufacturing. There's a lot of things out there that we do in the name of root cause, and sometimes it doesn't necessarily end up in the elimination of the problem. We're pretty good at the analysis part sometimes, but we don't actually eliminate it. So I want to talk a little bit about that whole process. The other thing I think I'd like to talk about today, and which I believe is really important, is how we drive the root cause process down to the craft level. In a lot of facilities I go to, root cause is the responsibility of the reliability engineers or another group, and we don't drive it deep enough into the organization. And we'll talk about that here in a little bit as well. Some of you may know us. Again, my company is Reliability Solutions. Our mission is to assist clients in achieving the profitable results through excellence in reliable manufacturing, and there's a lot of different ways we do that. We are also, this particular presentation I'm doing in conjunction with IDCON, who is a strategic alliance partner of us. We've been known throughout the years and continue to be well known for our what we do in the area of hard skills on the craft side of maintenance, operations, E&I, things like that. IDCON, we're sort of allied with work more on the work processes, planning and scheduling and things like that. This particular presentation is taking information from a class that we jointly put together a year or so, or a couple of years ago, that combines the process of root cause along with the forensics. So let's think about how root cause works in your facility. You know, you come into the morning meeting, there's a motor tripped out overnight causing a production loss. So everybody sits in the meeting and said, you know, what's going on? But very often the question isn't what, it's more like who. And usually the first question is, was it maintenance or was it an operational issue? And the very fact that the motor tripped out would indicate that, of course, can't be an operational problem, so therefore it's maintenance. So then we say, well, maintenance, who's responsible? And we look at that, and of course it's either going to be mechanical or E&I. And because it's a motor, that immediately eliminates anything mechanical. Then we go off and look at E&I, and of course it can't be an instrumentation problem, so it's definitely an electrical problem. So we go ahead and solve the problem by changing the motor, and it was an electrical problem, we go on our merry way. Well, of course, we all know, who's listening to this right now, that there are hundreds of different reasons as to why that motor might have tripped out, and only one of them might have been an electrical fault of some sort. What this really illustrates is human thinking. And as human beings, and again, since the dawn of time pretty much, whether it's the fear of flight mechanism that we're all born with or whatever, we are always very guilty of, with very little or almost no information at all, making a snap judgment. We all tend to rush to decisions. And again, it may be a primeval instinct based on how to survive or whatever, that we have to make this snap instinctive decision. Well, in the world of reliability, the same thing happens. Is we have an issue or have a problem, and we take a quick look at what's going on, and then immediately we make a decision. And we form an opinion of what we think is wrong. And the mistake then is we often verbalize that opinion. We tell somebody about it. Hey, I think it's this. I think the bearing failed because it didn't have grease in it. Or I think the bearing failed because we beat it on with a hammer or something like that. At that point, as soon as we vocalized that feeling or that word, we will then, any other piece of evidence that ever comes along, we will use to justify our opinion. In other words, we won't look at anything objectively. We're now trying to make sure that the evidence supports our pet theory. And this is a typical thinking process we see, which means that whenever a failure happens, the first question is who and not really what. What the thinking process should look like for good root cause is we should start out with some information. And I think that the most important thing to get out of the first part of this presentation is that good root cause analysis is a process of elimination. To prevent ourselves from jumping to conclusions, which is our natural instinct, we have to have a process in place that forces us not to do that. And that's this process of elimination.
Oh, Tim, I think I'm not hearing your sound anymore. Not sure if you muted yourself by accident or what. Sorry about this, folks. Hopefully you all can hear me. Tim, I don't know if you need to maybe plug in and try again here. Doug, are you hearing the audio?
No, I'm not. I just texted Tim.
Okay.
Reboot.
All right. Sorry, folks. This is we like doing these live, so we get the Q&A and things like that. But obviously, sometimes we're the victim of technology here. So just bear with us here a second. Hopefully, Tim can get logged out and logged back in. I know he is doing this from a client site, so sometimes the internet connections aren't always all that reliable. So just sit tight, folks. Hopefully we'll get this thing back up and running in a second.
Tim just texted and he's booting back in.
Okay.
Can you hear me, Doug?
There you are. Okay, cool.
I'm back.
You're back.
Sorry, guys. I think my network connection dropped out for some reason. For some reason, I'm losing.
Uh-oh.
My network. I lost my network connection, and I figure.
Yeah, you're kind of fading in and out. Well, I'm sorry, everybody. Hopefully we can get a solution to this here in a second. Hey, Tim, if you can hear me, maybe what we can try doing is you can send me your slides, and then maybe you can just call in to the webinar line, and that way you can do the voice part, and I can maybe advance the slides for you.
Okay, I can hear you now. Can you hear me now?
Yeah, I hear you.
Okay, let's just keep trying, and
Okay.
I think I'm good now.
Okay.
Plan B is I'll go to the phone. Okay.
Okay.
So we were talking about. I apologize, everybody, but I had some network issues, I think. We were talking about what the thinking process should like. We start off with information. We should brainstorm a good list of causes. Use a process of elimination to eliminate most of the causes down to the most likely. Then we need to brainstorm a good list of possible solutions. And then from the list, then again, process of elimination to pick the solutions. The big thing I think to understand is good root cause is a thinking process. And really, it doesn't matter what method you use, whether you're using PROACT or KT, Fishbone 5Y, it doesn't really matter. It's all about the thinking process. And all of the methods, no matter what software you use the same kind of thinking process because it's the right thing to do. And that is, first of all, identify or state your problem. Go out, collect some data, gather some information, some facts and some evidence. List your possible causes, okay? List the possible causes. Then through a process of elimination, reduce that list of possible causes to a small selection. Then perhaps go out and gather more data, verify the one you think is the issue, and then implement the solutions. A lot of times we tend to state the problem, collect the data, and we seem to get fixated on one particular cause and not broaden our minds, and that leads to analysis paralysis almost. There's an awful lot of tools out there, software-based tools to allow us to do root cause. Some of you may be familiar, for example, with 5Y, fishbone diagrams, Ishikawa diagrams, and all the rest of these logic trees and everything else. The important thing to understand is this is a thinking process, and some of these software tools actually get in the way of good thinking. We need to try to encourage our craftspeople, everybody within our organization, to use this sort of mental process. And the good news is that if you do that, then people are thinking a certain way as opposed to being slaves to the tool. The whole purpose of root cause is to do this, which is de-emotionalize the decision-making process. A lot of facilities I go to, you know, something bad happens, and immediately there's some kind of knee-jerk reaction, often involving, let's do a whole bunch of PMs on this machine because it's failed and we don't want to be bitten by it again. The problem with that is there's no logic, there's no science to what you're doing or why you're doing it, and very often it's personality driven. I go to places, well, why do you do it this way? Well, that's because we've always done it that way. And I'll cite a quote from Churchill. Actually, there was somebody before Churchill came up with it, but he's the one who's famously remembered for it. And if we don't learn from our history, then we're doomed to repeat it. And what I mean by that is, how many times have we had failures in our plant where it's failed, and then we replace the part or whatever, and then it fails again, and we replace the part again, and it fails again, and then usually at that point, well, we need to do some root cause, and we do a big root cause analysis. We think we determine the root cause of the problem, but we never implement the solutions. And of course, what happens again in a few 2 or 3 months is, of course, it fails again. One of the big issues as humans that we have is we think in patterns. And if you take a look at this slide right here and you start matching the people to the cars, I'll pretty much guarantee that everybody in the audience is gonna put the gentleman up here with a nice hat in number 1 there. He's going to put him right in the Buick over here. Probably going to put the the young guy in the middle in the Porsche, and the young lady there is going to go to the V-dub. Why do we think that way? And again, this comes back not to reliability or engineering. It's just the way human minds work. We tend to think in patterns. So, for example, I get a bearing fail in my plant. My immediate thought is, oh, it was a lubrication problem. So let's go fix the lubrication and whack a bunch of grease into it. And of course, most of us know that that's not the solution, but that's our natural instinct. So in root cause, we have to break these patterns of thought. We have to have a system, a science, a systematic way of breaking the thought process. So how do we break these thinking patterns? On the screen in front of you now, I hope you all see, is we have the step-by-step process. And again, it doesn't matter what method you're using, it will always follow these processes. On the left-hand side of the screen, you have the problems. Some facilities will have some kind of trigger process where we, some kind of event or some kind of trigger level, some threshold above which, if we get a certain amount of loss, we will then instigate a formal root cause analysis. Some facilities will say, you know, below X dollars, then we'll do an informal process. But there'll be some trigger, which is why we're doing the root cause in the first place. The next part of the process, again, we need to determine a problem statement. And what is the problem? We'll talk about that in just a minute. Then we come to possible causes. We list all the possible causes. Then this next step is we select the most likely causes. Once we have the most likely causes, we go to solutions. And notice there it's solutions, not solution. List several possible solutions. And then from that, we narrow that list down and select the most appropriate solution. And then finally, eliminate the problems. A lot of times, we do pretty well in the first part of this, possibly to here, to the selecting the most likely cause, but then we really neglect the back end of this diagram. We show in the diagram data collection happening around possible causes, but in reality, in the practice of this thing, data collection is going to occur throughout the entire cycle of your root cause. So some basic ground rules on RCPE. First of all, we believe that it's a process, this simple RCP process we're talking about today, can handle 80 to 90% of all the problems. Again, if we use the thinking process and perhaps a couple of the simple tools we'll talk about in a minute, this will get you 80 to 90% of all your issues, okay? It's also simple enough that it can be implemented and applied on the front line, okay? We look at best-in-class organizations, about 30% of all the man-hours within the organization are used for doing RCPE in one form or another, whether that's the big formal investigation because we've had a major event, or whether that's frontline mechanics using RCPE to try to figure out why the hydraulic pump failed, or an operator trying to figure out why the pump's cavitating at an informal level. About 30%, a third of your time should be spent doing root cause. Because remember, it's only when you understand the root cause of the problem can you take steps to eliminate it. Another thing, we believe that large teams, you know, and I define large, well, four or so people or more for problem solving are not always necessary or effective. Certainly on the big, complex issues that you run into in various plants, then a team is appropriate. But there's an awful lot of day-to-day events and smaller events that occur that can be solved by one or two people. Now, it's always good to have different perspectives, particularly in the more complex problems that maybe involve maintenance and operations. It's always important to ensure that we've got a good team there. But for the simple day-to-day stuff, you don't need a big team. RCPE is a matter of two types of thinking, critical and creative, and I'll talk about those in just a minute. And the software programs are just that. The documentation methods are just tools to document what you did. The core of root cause is the thinking process that goes on behind it. Okay? So I mentioned earlier critical and creative thinking, and in root cause, we need both types of thinking. There are certain times within the root cause where we need the creative type mind, For example, if I'm trying to brainstorm all the ways this machine could fail, creative thinking is definitely the top of the list there. And typically creative thinking is based on experience, ideas, objects, and things like that. The other type of thinking that's vital is critical thinking. And critical thinking is the analytical process. So, you know, I use my creative part of my brain to come up with a list of all the things it could be. I then use the analytical part of my brain to look at the facts that exist and tie those to my evidence and tie those to my possible brainstorm list and use it to eliminate. In any root cause, we need both types of thinking. And obviously, within our human family, there are people who are better at creative, and there are people who are better or lean more towards the critical thinking. It's important that if you are putting a team together, you have both, because both are going to be used at some point during your root cause. Okay? Creative thinking we're going to use to brainstorm, and certainly if we have those of us who have an engineering type background where we're taught throughout our early careers and our learning to just deal with facts, sometimes the creative thought process can be difficult. But you know, creative thinking can be practiced, and we can use creative thinking to there are various sort of mental workouts and brain games you can use to get out of your pre-programmed packaging, your pre-programmed thinking. Critical thinking is the opposite. Critical thinking is the opposite, and this is how we work through the complexity of the problem, and a lot of it is to do with endurance. And really, when we're critical thinking is all about the reason part of it, and how we explain the cause and effect. And again, when we start to build this, and I'm going to show you a diagram in a minute of how you sort of lay this thinking out, the critical thinking is our process of elimination. The other thing that we must do in the critical thinking part is to distinguish between facts and perception. Between facts and perception. A lot of times we'll do analysis, excuse me, based on information that is provided to us. And one of the things that's absolutely vital if you're going to succeed and get a successful resolution in your root cause is to make sure you turn that information and that data into facts. If we use the analogy of crime and crime scene investigation and things like that, we can, you know, the police or whoever it is, law enforcement people, will interview people, but they won't take that interview as fact until they've corroborated that interview with other information. And that's really the difference between perception and facts. When an event happens, people will have a perception about what they thought happened. It's valuable information, but it doesn't automatically mean that was the fact. A good example of that is, you know, my operator said they thought talking to an operator about a steam leak. Oh yeah, we have a 1/4 of an inch hole in the pipe. Well, the reality is that really a fact? Because how did they measure the hole, right? What they saw was a steam leak coming out of the pipe. They don't know it was a 1/4 inch hole. Remember, this is all about a process of elimination. Again, the old Sherlock Holmes novels are a good analogy to this. So in terms of the start of the process, the trigger, in facilities we can have a formal trigger, and there'll be a hurdle rate or some value, environmental safety perhaps, direct cost of downtime. If it's above this level, the loss, then we will instigate what we call a formal analysis process. Now we can use the same thinking, but we're going to be more formal. We're going to put a bigger team together and address the issue. But there are also the frontline RCPEs is less formal. And this really needs to be part of your daily work. As a mechanic goes about his business or her business, maintaining a piece of equipment, I'm going to change the bearing out. Now, when the old bearing comes out, very often all that happens is it gets thrown in the dumpster. Or the old pump comes out and it gets thrown in the dumpster. Or the old hydraulic cylinder just gets thrown away. There is evidence within that information that could tell us exactly why that cylinder failed. And there's absolutely no reason why a mechanic or an operator or someone on the front line can't look at that evidence and determine what the problem was. Once we know what the problem is, we can then prevent the problem from happening again. I have some clients where before an operator submits a work request to have a piece of equipment looked at or fixed, that work request has to be accompanied by a root cause document, a simple root cause analysis. So instead of the typical work request you might get for an operator saying the pump quit, maybe the new work request says, the pump is not pumping due to a plugged strainer, or some form of analysis has been done. As we said earlier, mechanics, technicians, I&E techs working on specific problems in your facilities, there's no reason why they can't be empowered to do more failure analysis. We have become a generation of parts changes. Something breaks, we change the part. And what passes today for troubleshooting is often just a whole bunch of parts changing. I challenge each of you listening to go back to your facilities and look at how people, for example, troubleshoot hydraulic systems today. Typically what's going to happen is people are going to have a problem. They're going to maybe tweak on a couple of pressure valves first, and if that doesn't work, they'll just start changing pumps. They'll change valve blocks. They'll change pieces without the troubleshooting. A couple of years ago, I did an article or a paper at Ultrasound World on using condition monitoring, particularly ultrasound, in troubleshooting hydraulics. I can tell whether the valve is leaking, or I can tell issues. So it's very important that we don't just change those parts. The problem statement is really pretty important, and sometimes we're not good at that. For example, Keith Richards never had a problem with drugs. The only problem he really had was with the police. And again, he'll be well preserved still, I'm sure. Regarding writing a problem statement, first of all, there should be one object and one problem. Okay? We need an object and a problem. So it has to be, whatever the problem is, it has to be a fact. And it's got to somehow relate to our trigger, so we answer the so what, who cares question. And it's a good idea to try to keep it simple. For example, the hydraulic system's not working. Well, is that a fact? Is it one object or one problem? The hydraulic system is a very complex issue. Perhaps a better example would be the hydraulic cylinder is not extending fast enough. If you look at those two statements, not working versus not extending fast enough, the second of those two statements has got something I can get my teeth into. Okay, so really important how we write our problem statement. You always need to make sure you're looking for the right thing, and that's what a good problem statement does. Is the problem that I've lost my key? Or is the problem really I can't get into the house? Right? I can solve the key loss thing, but does that always necessarily get me back into the house? We don't have enough resources to manage our materials. Is that really the issue, or is the fact that we don't have any bill of materials in our CMMS program? The root cause of the problem is we don't have the bill of materials. We're not well trained in alignment. Or are we losing too many bearings? Right? The real issue, the fact that we're not trained in alignment doesn't matter. If we don't have any misalignment, we don't need to be trained in alignment. What we really need to do is stop our bearings failing. Here's an example of a problem statement we've seen before, or someone has written at some point. The pump is not delivering enough flow. It sounds as if it's cavitating and the bearings are hot. When you actually look at that, what's the real problem? As an operator or as a plant, my real problem is it doesn't matter if it sounds like it's cavitating. It really doesn't matter if the bearings are hot just yet. What really matters is it's not delivering enough flow. And in fact, the other two items are probably symptoms. A hot bearing is really a symptom of something else. The hot bearing could be a symptom of the cavitation. So we've got to make sure when we write our problem statement that we're writing it about one item and one problem. Don't try to build too many symptoms in there. The next thing we need to do is start collecting evidence, and the facts that we need to collect are, what, where, when, are the obvious ones. What exactly happened? Where did it happen? When did it happen? Changes in time, what's happened previously, and other similar objects to comparison. Those are our sort of 5 base things. So I'm going to ask what happened, what was the environment, what was the conditions, or what were the conditions that were going on at the time of the failure, or when it was first noticed. When is it important? A timeline, putting together a timeline is an extremely valuable tool in solving problems. Nowadays, of course, with a lot of our processes, we have Pi and PlantView and a variety of other tools to capture that information. Your vibration trend is always a good example of looking how things changed over time. Looking at how ultrasound, when did the dB value start creeping up? Again, another valuable change in time there. This is just an example of a tool that we have that we use, our evidence collection vest. This could be a toolbox, it's just as easy as it can be a vest. But these are the things we need to collect the information. A digital camera, pocket voice recorder. Nowadays, they all masquerade as a smartphone, and to be quite honest, most of your modern smartphones have great capabilities. The optical sensors in them are really good. They're actually a pretty decent camera. Flashlights, a couple of different flashlights, notebook tape and tags are in this pocket here. Probably this thing right here, this little 10-power magnifying loop to look at fracture faces on the forensic side is very important. A laser pointer, paint markers. That whole thing is probably, maybe $50 worth of gear. But what you've got there is a really good little evidence collection kit. My question to each of you listening today is how many of your facilities have that go box, or that crash kit, as we could call it? Remember, we have to think about facts, and we need to, in our world of root cause, be dealing in facts, not just information. If you take a look at this statement here, you can see that, well, you read it, but as you look at that, a lot of people might see the information presented says something about jumping to conclusions, right? And that certainly looks like good information right here until we actually look at the facts, right? So whenever you're presented doing root cause, whenever somebody presents you with some good information, you need to find a way to validate that and make that a fact, turn it from a good piece of information into a fact. Once we have the initial data, we then need to put our creative thinking hat on, and we now start to think about possible causes. And the key letter here is the causes, the S on the end. One of the things with 5Y, and many of you may be familiar with the 5Y methodology, you ask the question why 5 times and you get to the root cause. One of the issues with that method is when you ask the question why, it automatically implies that we go to one place. If you would change that phrase and just instead of asking why, ask the words how can, automatically you're going to open yourself up to many different possibilities. So you have your evidence, and based on the evidence that you have, you should ask yourself the question, how can this happen? How can? Once you have this nice list of potentials based on your evidence, you can then use evidence to eliminate. And again, it supports our process of elimination. Okay? The problem with Y and 5Y is it tends to narrow our thinking, and inevitably we will miss the real root cause. It's also important between each level of our how-can diagram, and I'll show you one of those in a minute, that we have a clear cause and effect relationship between each level. The items on your list should contain an object and a verb, okay? And it's useful if, again, in a bigger complex problem, is having a diverse group to do this activity. It can be done alone, but it's a lot better with a diverse group. So how do we document that? One way is to use sticky notes. It's a really simple approach. So what we have here on the whiteboard are sticky notes with our, this right here would be our problem statement, or perhaps our trigger. Here's the problem statement, and then we say, well, how can that problem happen? And we've got 4 things here. So we take these in turn, well, how can that happen? And we drive it out deeper and deeper. You can do it simply on a blackboard. Here you've got a bunch of craftsmen, actually from a mine, working through a problem. Very, very simple. It's not high-tech at all. It also doesn't distract from the thinking process. What you typically find here is that at some point going down into this diagram, we need to swap a couple of these around, and of course with them being sticky notes, it's real easy to change. Yeah, I can do this stuff in Visio or other software packages, but it's a little harder to make the swap and make the switch, and somehow we get distracted from our thinking processes. So a whiteboard here is great. A glass board, you know, and the see-through whiteboards is good as well. This is an example of a software tool. It's called Simple Mind that we use. It's, you know, I think it's a free app for the iPad, or, you know, $20 for the desktop version. Just to show you how the how-can diagram works. So here's my problem statement. The Titanic sank. So why did the Titanic sink? And when I ask people why it sank, just about everybody in the room is going to tell me because it hit an iceberg. The question I have, is that really why the Titanic sank? Because there's icebreakers every day throughout the world driving over icebergs and they don't sink. So why did the Titanic sink? So we look at the how-can diagram. This would be my trigger. 1,500 people died, a very tragic accident. The Titanic sank. But the only reason, there is only one reason why the Titanic sank. There's only one reason why any ship sinks. It's because the water filled the whole hull. So in the case of the Titanic, we ask ourselves, how can the water fill the hull? Well, there's two things that needed to occur for the water to fill the hull. We had to have a big hole in the hull, but at the same time, the Titanic was designed so that she had watertight bulkheads in her. And if those watertight bulkheads had been sealed, the hole in the hull wouldn't have been a factor. But what we had, as we often do in these big tragedies, is two things aligned. So you see the little and sign there. So I had to have an opening in the hull and the bulkheads not being sealed. So my next question is, how do I have the opening in the hull? Well, two ways I can get a hole in the hull. First of all, we bump into something and the hull wasn't of adequate design, wasn't strong enough, or I bump into something so hard that it doesn't matter what the design is. And of course, this was one of the issues with the Titanic, that they could never guarantee the design of the hull. And in fact, until that guy went down and pulled pieces of metal off the bottom of the ocean, and they could do metallurgical testing on the rivets and the metal, they could never really eliminate this. But if I take these now and punch those out one level deeper, strength of the hull could be due to the strength of the steel or the strength of the rivets. The outer force exceeds the strength of the hull. That's because I hit the iceberg hard enough to create the opening. So we see how this is all a cause and effect. How did water fill the hull? Because I had an opening in the hull. How did I get an opening in the hull? Because I had an outer force that exceeded the strength. How did I get that? Because I hit the iceberg hard enough. So I take this a level deeper. How did I hit the iceberg hard enough? I didn't turn quickly out of the way, and I was traveling too fast. Those two things. If I'd have hit it slowly, wouldn't have been a problem. Okay? So if I'd hit it slowly, it wouldn't have been a problem. If I didn't hit it at all, it wouldn't have been a problem. How come I didn't turn quickly enough? Well, the steering failed, or I didn't know anything about the presence of the iceberg. Steering didn't fail, but we didn't know the iceberg was there, and we were going in fog. And you can keep on driving it out that way. So this is just a little tool to do that. I can produce this very simply with sticky notes as well. Okay? Process of elimination. So now I have my how-can diagram. I can come back through all of these and start Xing them out. And you can see here we've eliminated the design of the hull. We could eliminate actually steering. It failed. Okay? And then we're left with the possible causes. Possible causes was we didn't know the iceberg was there because our lookout didn't see it. We were in fog, and we were traveling too fast. Okay? So we use logic, deduction, reasoning, critical thinking to eliminate things, and we end up with our problem. The good news about using a tool like this is it lays out your thinking process so that when you get to the solution, you've not just got the solution, you've also got how you got there. This is just an example. Just you know, these can get pretty complicated. This is a problem I was involved with last year on some coupling bolt failures as we drove through the potential problems. And again, it's just to show you how these things lay out. Again, whether it's a piece of computer software or whether it's a sticky note on a whiteboard, the basic principle is just the same. It's very important as we go through our failure that we look for all three root causes. In any problem, there will always be three causes. The first cause will be the technical root. Okay, for example, we hit the iceberg and put a hole in the hull and didn't have the bulkhead seal. The second cause will be the human factor, the human element. In this case, the lookout didn't tell us the iceberg was there, the captain was going too fast. And most importantly, there will also be a work process element, the work element. And this is the work system or the work process that was there or was not there that allowed the human to behave the way they did. In the case of the Titanic, the captain was under a lot of pressure from the company to achieve a fast crossing. Very important. We're real good at getting technical. We can get to the technical facts pretty quickly. But unless you get to the human or the work process and solve those and eliminate those problems, find out why the humans did what they did and put processes in place to prevent that, we will never, ever completely solve the problem. When we get to solutions, again, selecting or first of all, brainstorming solutions is again an exercise in creative thinking. We put our creative hat on. And what we're trying to do is not just pick the first solution that comes to mind, but look at the several options that we have. And then we want to select these by which is the most effective, which is the most efficient, which is technically feasible and worth doing. And we always need to consider the cost that we're going to spend to solve the problem versus the cost of the failure itself. And if the cost of the failure exceeds the cost it's going to be to solve it, then you need to come up with another solution. Or better yet, just let it fail, because it's obviously not going to do much good. In terms of problem elimination and how we eliminate the problem, again, some of the questions we're going to ask ourselves: is this a one-time fix, maybe a redesign? Or does it require me to do some different kind of on-condition tasks? If you've done a good job of the root cause problem and the how-can diagram, that how-can diagram should lay out and help you and guide you in this. Our guiding principles are, again, sensible, defensible. Is what you propose to do sensible and defensible? Is it technically feasible and worth doing? And what does it cost to prevent the failure versus what's the consequence of the failure? We really don't do a good job in these cases of justifying and showing the value proposition or the business case. And so what happens at the end of the day in a typical plant or many plants is we go through this analysis, we take our time, we do a really good job of the analysis, but we never end up getting these solutions implemented. And the reason we don't get them implemented in many cases is because we haven't done a good job of showing the powers that be what's in it for me. Show me the money. What I'd like to do now is switch gears. We've talked a little bit about the process now. I've got a couple of 3 minutes left, I guess, or a few minutes left. I want to talk about the forensics, because we can learn the process and we can do it on sticky notes. But really, if we want to really empower our craftspeople, we have to understand the forensics. And this is an area where a lot of people have resistance to getting involved in root cause, because they think, well, as soon as you mention forensics, we've got to have a lab, we've got to have a scanning electron microscope, and a whole bunch of other fancy tools that, you know, we just either can't afford or we can't afford to train people to use effectively. And when you talk about the word forensics, it doesn't have to be that sophisticated and complicated. Every time your mechanics operators in the process of doing what they do every day do work, there are little pieces of evidence, little items that they can notice or pick up on, often with a naked eye, that will go a long way to telling us what caused the problem. Let's just take an example. Let's talk about rolling element bearing failures. A lot of times, you know, facilities we go, if bearing has failed, it goes straight to the dumpster. We don't do anything with it. Critical failures, big expensive critical machines, we may send the bearing off to our bearing manufacturer for analysis. But there's an awful lot we can do day to day with our normal bearings that will help us. One thing is, if we're disassembling bearings, let's have an area to do it. let's have a nice area, preferably natural light, but well-lit area. We don't really want to use sodium lights or incandescents because they put an orange hue on everything, and sometimes we're looking for those colors to tell us what's wrong. Another thing I encourage is, as we're disassembling our bearings and we're cutting them in half and we're inspecting them, is photograph the process or video it. A lot of times I do this, you know, obviously I do a lot of this myself, and you know, I'm in a root cause mode. I've got my Sherlock Holmes hat on and the big pipe and everything, and I'm looking at this bearing and I'm thinking what could be going on and listing possible causes and stuff. And even though I'm fully attuned to looking for evidence, if I've photographed the disassembly and then later on, a few hours or a day or so later, I go back and look at the pictures, I'll almost guarantee I'll see 3 or 4 things that I see in the photographs that I didn't actually see live, as it were. Okay, so it's very important we disassemble that. Another thing that's important is, as I'm pulling the bearing out of the housing, I mark the location of any grease zerks, grease fittings, mark the relative locations of the housing, how the inner ring and outer ring were located in the housing. That's essential to understanding the wear tracks and everything in the bearing, and it's something that's very rarely done. You know, it can be as simple as a mechanic putting a dot on a race as they disassemble the machine, and it can tell you huge amounts of information as to why the bearing failed. A lot of times when we have a bearing that's failed, we tend to leap for a cutting torch to cut it free and get the machine up and running. The problem we have with a cutting torch is it does a huge amount of collateral damage. So now it's very, very hard to discern what happened. A disc grinder and a chisel is basically as quick as a cutting torch, but it's still intrusive, but a lot less intrusive than the torch itself. Another thing that often happens is people want to clean parts, and particularly with bearings, you need to do your inspection before they're cleaned, because there may be something that you're looking at with the dirt and the grease and everything else that may provide vital evidence as to why that bearing failed. So we need to have that information. In terms of inspection, again, inspect with either the unaided eye or no more than a 10-pound magnifier. You can pick up that little loop from Amazon for, you know, 20 bucks or something, a little 10-pound magnifier. 90% of everything you do in looking at fracture faces and failed parts is 10 is all you need, 10 pound. When we're talking photography, nowadays, a couple of tips on photography. The sensors we have on modern smartphones are of such good quality now that you don't need a high-end digital SLR, so long as you light it correctly. What you're looking at here is a fracture face. It's actually a part of a large spherical roller out of a roller bearing, probably, I don't know, 3 or 4 inches in length. So it's a pretty good size roller. And you can see in the top sort of right-hand corner here, there looks to be some kind of features on that fracture face. Now look what happens when I illuminate it from the side. And all I've done is get an LED flashlight, you know, a little inexpensive LED, and illuminate it from the side, oblique lighting. And you can see immediately how these fatigue fractures show up and just pop off that face. If I go back, you can see the difference there pretty clearly. So good lighting and a camera is really great. So, talking about bearing failures, you know, there's a lot of terms available that we use around the failing of bearings, and probably one of the most common here is spalling. And when I see bearing failure reports and I see the report saying bearing failed due to spalling, it's really like, tell me something else that I don't already know, because the reality is that just about 99% of all bearing failures, no matter what happens, will all end up at spalling. This is a good example of spalling. This is that characteristic pattern, sometimes called fatigue failure of the surface and everything else. This is the end game. Just about no matter what causes the bearing to fail, what the initiating problem was, they all end up here. All roads lead to spalling. So the majority of failures will be spalled. The trick is, how do we catch them before they get to this stage? Because at this stage, all of the initial evidence has gone away. We need to use vibration analysis. We need to use our various condition monitoring techniques. Ultrasound is a great technique here. to catch these failures early on in the failure mechanism and catch them before the damage has gotten this far, because by the time it gets here, a lot of the initial reason as to why this happened has been lost. So again, we need to capture bearing failures before they get to be spalled. Here's how a bearing spall occurs. Now this is effectively what we're looking at here. This is the surface of the bearing, and you have these microscopic, minuscule little subsurface flaws. As balls and rollers roll over this, it flexes the metal slightly, and that leads to subsurface fatigue cracking. Okay? The normal end of life for a bearing, this is what happens. These little tiny subsurface defects form fractures, and the fractures get bigger, and eventually that fracture gets to the surface. That process for a properly installed, well-lubricated bearing should be 20, 25 years or more. Of course, what happens is we prematurely fail these bearings. So our failures actually start at the surface due to some surface imperfection and then work down. But this is the traditional view of where spalling comes from. The end result is it's always going to be spalled. But we need to know whether it started on the surface or whether it started subsurface. Okay? By capturing the bearing when I can see changes in ultrasound or when I can see changes in vibration, we get the early warning that we need. So let's just talk about some of the potentials. And again, in our full-blown class, this is sort of a day's worth of information we're talking about here. So we're going through this a little bit fast, but just to give you some examples of what we can see. One of the causes of that surface damage, which then leads to fatigue, is called Brinelling, or true Brinelling. And true Brinelling is where the race has actually been indented here. So I've actually got indentations in the races. Okay? Now this is a section, or this is a part of the bearing. This is actually a single row deep groove ball bearing. In this bearing, the roller this ball is designed to run right down here, right down the middle. So the fact that I have damage indented to the side here tells me a lot about what caused that. First of all, if the motor had been dropped or the machine had been dropped vertically, the damage would have been sitting here in the middle of the race where it normally should be. So the fact that the damage is on the axial loaded side of the race, what does that tell you? How did that damage occur? We could have dropped the motor on its end, but that's not likely. The most likely cause of this is somebody beat that bearing on with a hammer using an incorrect procedure. So the location here tells us the cause. True Brinelling, the material is displaced. False Brinelling is the removal of metal, and again, it's spaced at roller spacing, and you can see here across my race I've got polish marks. Okay, it's called false Brinelling. The only thing, one of the few things that causes that is external vibration when the bearing is stationary. Now this again is a ball bearing. The fact that that race is centered on, that damage is centered on the race tells me that that damage was done in service while this machine was on standby and not operating. Many people store their bearings flat. So if that damage had been done in the warehouse, I would have expected to see the damage down here on the side of the race. So again, the marks tell me what causes the problem. Their location tells me why. Now, if I don't do anything about that, I can see that in ultrasound. I should be able to see that pattern there happening in vibration. If I choose to do nothing about it, where does it end up? Yeah, you got it. It ends up there. Now, I can't tell you whether that was true, false, or whatever. So it's very important when we get the first indications of bearing failure, we get that bearing out of there early enough. This is another common failure that we see, and this is called smearing. It's caused when the rollers don't roll but actually skid and slide. By the way, when this happens, it's happening because you've got too high a viscosity, and so the rollers can no longer roll. They actually skid, and it basically takes metal and smears it and redeposits. This creates, by the way, large amounts of ultrasound, huge amounts of ultrasound. It can also be caused by too light a load. Again, left unattended, this all ends up at spalling. One of the most common causes of failure that we see outside of lubrication is incorrect fit. We in North America particularly, but all over the world, do a terrible job of fitting parts together, and particularly installing bearings. When bearings have been installed with too loose a fit, you get a very characteristic pattern. In this case, we're looking at creep or fretting. Very, very characteristic. You can just take a glance at the shaft or the bearing and almost immediately know they had an installation issue right there. Another common source of failure is water ingress. And again, there's 30 or 40 different things we should talk about here, but I'm only doing a few of them, just some highlights. But again, water ingress itself gives you characteristic markings on the outer part of the race. And this is one way that corrosion shows up, these black stains. This encases a tapered roller bearing, and you can actually see, looking at this pattern right here in the bottom left, is there's actually two sets of marks. What this tells me is this machine actually was contaminated in a stationary condition twice. So this was probably a machine that was installed, left sitting, got wet, got corroded, ran, came back a few months later, stopped, sit, got wet. So there's been two events where it got corroded in this particular case. A longer term problem, not a short term problem. So there's a couple of little things we can see forensically around bearings. Again, to see this stuff, it's probably 5 minutes work with an angle grinder to split the bearing. You don't need a PhD in metallurgical science to be able to analyze this stuff. Any craftsperson can do it. When we talk about fasteners, we talk about threaded fastener failures. Probably the most common type of failure is incorrect tension. The mistake everybody makes with fasteners, though, is they assume that the tension is because, or the incorrect tension is because it's too tight. It's too tight. The reality is 90% or so, a significant percentage of fasteners fail because of fatigue, and that tells me it's too loose. So how do I tell the difference between a fatigue failure and an overload failure? First of all, when I'm looking at fractures and fracture faces, rule number one, the crack will always grow perpendicular to the plane of maximum stress. So if I have a bolt that is in tension, or anything that is in tension, it will grow crossways, like this. If I have it failing due to internal pressure, the maximum stress, or the crack will develop this way, perpendicular to the maximum stress, which is acting this way. Think about a boiler tube that splits. It always splits longitudinally. My first question when I look at a fracture face is overload or fatigue. On the left-hand side here, you have signs of fatigue with the progression marks. This one on the right-hand side is an overload. This happened over time, over a period of time. This happened instantaneously. Fatigue failure on a fastener, which this is invariably caused through a lack of tension. Not too much tension, but a lack of tension. Okay? Overload failures, crystalline, it's an immediate instantaneous failure. Probably 70% of all your failures are fatigue related. One of the things with an instantaneous failure, you'll have these chevron marks. If I go back one slide, you can see chevron marks pointing towards the origin. This fracture started here. In this case, this is a cylindrical failure on a pipe. The chevron marks point to the origin, which was somewhere over here. In this case, my chevron marks are pointing to an origin that was somewhere to the right. When we have a fatigue failure, what you'll see is an initiation point. We'll see a series of progression or beach marks. And then right here, we have what we call the instantaneous zone. This is where the final fracture occurred. So this is an overload fracture of this area. This is my fatigue area. The relative size of that overload fracture tells me how much load this thing was under when it failed. And by bisecting the fatigue marks, that tells me the origin is right there. So this fracture, when it failed, started right there. In this case, you can see a little bit of damage, which was probably the stress razor that caused the initial problem. The fact that I've only got about a third of this face is instantaneous means that this was probably about a third of the rated load of that shaft when it failed. Here's an example here of another fracture. I've got two fatigue zones. This is one. This is the other. This is the instantaneous zone. And the fact that I've got two fatigue zones on opposite sides tells me this was reverse bending. In other words, this was bending back and forth just like you do a paperclip. These marks around the periphery that you see are what we call ratchet marks, and those are the stress razors. So the fatigue fractures started at each one of these marks. You've got the same thing over here on this crank. A lot of people wanted to blame this on this particular failure on that oil hole as the starter, but actually it was this radius right here, the equivalent of this radius here, that was incorrect, and that's where our failure started. So again, forensically speaking, I don't need a scanning electron microscope to see this. I can look at this with a good quality magnifier. So just to sort of talk a little bit about who should do root cause, given that the science is not that complicated, craftspeople should be empowered to do this and expected to do this. When the problem gets to a more serious, complex problem with a higher trigger level, then we go to an area or a plant team. But we need to get our craftspeople more empowered and involved at the craft level. So just to kind of summarize real quick, I know I'm getting the hook from Doug and Maureen, but first of all, RCP is a structured approach. It has to be systematic, scientific. This is not emotion-based. We need to remove emotion from the process. It is a thinking process. Documentation tools are available, but keep those documentation tools simple. We can use sticky notes. We can use simple tools. Don't become slaves to the documentation system. Simple RCP principles should be applied by your frontline employees. Start preserving parts for inspection. I can't count the number of times where I've been asked to go to a site to assist in problems, and I go find evidence by dumpster diving. Now, it's good fun, dumpster diving. You pick out all kinds of good broken parts in there, but it's a lot better if people are preserving the evidence up front. Get lay-down tables where these things can be put down. 10 times magnification reveals a heck of a lot of information about fractures and the forensics of it. And RCBE should be integrated into everyone's work function. Everybody has a role to play. So in conclusion, I'm going to let Maureen take over here, but thanks for attending. I'll hopefully see some of you at Reliable Asset World in a couple of weeks. My contact information is there, phone number and website, and my email is probably the best way to get a hold of me. Hopefully you've got some good stuff out of this, and again, thanks for listening.
Awesome. Well, I know we've hit the 2 o'clock, so obviously those of you that need to jump and get back to the office, no problem, and we thank you for joining us. There were just a couple questions, and the folks that asked them are still online, so let me just toss these to you real quick, Tim, and then any additional questions we'll get to Tim, and he can follow up with you guys one-on-one to get those answered. But a couple people asked, you had mentioned an iPad app, and a couple people were asking you to restate again which app that was so they could make note of it.
The app is called Simple Mind mapping software. It's called Simple Mind. We don't make it or anything like that. There is a free version and there's a paid version for, I think, $5 or something. They also have a desktop version, which then you can integrate your iPad data into your desktop, which we use. It's available for both Mac and PC. Great little tool, very effective, and it's of all of the ones out there, it's really, really, really easy to use. So you don't concentrate on format. You can just go ahead and do it. So we use that quite a bit.
Okay, cool. That knocked out a couple people asked the same thing there. Then someone else was talking about incidents. The majority of incidents in aviation and maritime industries are, human factors are related. So the question was, why wouldn't you start with human instead of technical in those instances, or would you?
It's certainly depending on the nature of the failure. It depends on the failure. Yes, it could well be human. From the reliability perspective, typically there is some sort of physical, technical thing that's happened. The pump quit working, the bearing seized up or something, which is the start of it. And as engineers, and again in industry, we tend to think technically already. And so, yeah, I agree totally. We really need to spend more time on the human element. In fact, I just wrote an article for publication here in a couple of 3 weeks on the psychology and the human part of reliability, because it's an area that's largely ignored. When I look at root cause and people doing root cause today, they're great at getting to the technical side, but they're exactly right. We don't go deep enough to get to the human side. So usually the technical part will help us drive to the human part in again, machinery and industrial reliability anyway.
Perfect. And then a couple folks had been asking throughout about, archiving this presentation. So we did record this. We will put it up on our website, uesystems.com, in the online learning section. So you can take a look at that again there. And, Tim, as you can see, he's got his email address up there. So if you are looking for specific slides or the deck or whatever, you can just shoot him an email and see what he can provide to you there. And then there are still a couple other questions, but I think, Tim, in the interest of everybody's time and your time as well, we'll just get those to you, and you can just follow up, hopefully, as you have time, with these folks on a one-on-one basis, if you don't mind.
You bet. I can certainly do that, and welcome the opportunity. So.
Very good. All right. Well, we will let everybody go. Just again, reminder, Tim is going to be at our Reliable Asset World Conference, which is taking place June 1st through the 5th. We're really looking forward to it. Time is kind of tight, but if anybody still has the potential to come join us, just let us know and we'll take care of you. Tim, thanks so much again for participating today, and to all of you that signed on. And I hope everybody enjoys the rest of their day and enjoys the Memorial Day weekend.